Hello everyone. Okay, this video is going to be a short video. Okay, and this video just show you the calculation of shear stress on the torsional torque-loaded member. Okay, and the calculation of shear stress on the shear stress for the rod on a subject to a torsional torque, not the torsional torque-loaded member. Okay. Under talk, yeah, actually it's very easy. Yeah, we have if in the PowerPoint slide we have in the PowerPoint slide it shows very clear that the torsion, the shear stress at the cross section area as the cross the shear stress at the cross section area of the torque loaded member is. Okay, this is shear stress and equal to T and is rho over J. Okay, and T is the torque and rho is the distance from the center and J is the polar moment of area. Okay, and they say, okay, there's a shift. Okay, and this shift is subject to a multiple external load. Okay, and then he want to calculate a shear stress at a certain cross section. He say AA is here. Okay, he want to calculate the shear stress divided at the section AA. Okay, section AA is here. Okay, and section AA here is a zoom in of AA section. Okay, this is AA section. And you say in AA section and the point A and point B on AA section, what's the difference between the A and B point? A is at the surface. Okay, let me draw this picture. Okay, for this cross section, doesn't like a sphere. Okay, R small too small. Yeah, this one. Okay, A is here. A is Okay, A is here. A is here. A is at the surface. And where is the B? Okay, B is. Let's look at where is B. Okay, so B is here, and B is. Yeah, what's the distance? B is 0.015 meter. Yes, very small. Okay, say B is here. Okay, and here is 0.015 meter. And here is at the surface, it give us a radius of the cross section. Okay, it is 0.075 meter. Okay, so that's the difference between A and B. A is 0.057 from the center. So yeah, simply speaking at the surface. And B is 0.015 meter away from the center. Okay, so it tell you that rho A and rho B are different. Okay, and the J, yeah, we have the cross section area here. The J. J is a polar moment of inertia, so we can calculate the polar moment of inertia. First, okay, what's the cross section? It give you the radius, right? So to give the radius, okay, so you have the R out power 4 minus RI power 4. And I don't, because this is solid, so there is no RI, so RI equal to 0. So the polar moment of area is, and RO, R out is 0.075. 0.075 and to the power 4. Okay, that's J. That's the polar moment area of this core section. Okay, so another thing we left is the torque at the AA section. So how to find a torque of AA section? Yeah, we need to use once again the cut section method. So here is the cut section from the textbook. Okay, we'll cut the AA section here. And here the textbook already assumed the torque at AA section is clockwise. But my habit is I want to assume everything is counterclockwise. To me, it's more convenient, so I assume T is counterclockwise. Okay. And then calculate from the left. Okay, so in this problem, for such mechanics analysis, I mentioned lots of before, you calculate from the left or calculate from the right, you have the same answer, but maybe the direction is different. Okay, so I did the section, okay, AA section, do the rigid body equilibrium. In this problem, we only have to consider the moment balance. Okay, so the moment, okay, we have 4.5 kilonewton, okay, and it's counterclockwise, so it's positive, and it's 3 kilonewton times meter, and it's clockwise, so it's negative. And assume t equal to 0. So what's our t is? Our t is minus 1.25. And don't forget the unit. Our unit is kilonewton times meters. It's kilonewton times meter. Okay. So initially we assume it's counterclockwise. Counterclockwise. Initially we assume counterclockwise, and we'll get negative value. Yeah, and then the real let's mean the real direction is clockwise. Okay, so yeah, the same as the textbook, right? Okay, but if I don't know the direction in advance, so I like to assume everything is positive. Okay, so we have the torque at the AA section. Okay, so and then we can calculate the shear stress at this section AA. We calculate A first. We'll calculate A first. Okay, shear stress A, we need to know the torque and the rho A and the J. Okay, the torque. Okay, here be careful. The unit it's actually for the shear stress. I'm not sure the direction will really make the answer difference or not. Okay, so. Okay, let's keep the negative. Okay, but I think I don't answer. This won't affect the answer. And here is kilonewton times meter. I want everything in newton and meter, so I times to 10 to the power 3. Okay, and the rho A is a surface, so A is 0.05, 0.075 meter, and the J is pi over 2 and 0.075 to the power 4. Okay, so what's the I think the J, here is my notes. My J is 4.968 times to 10 to the power minus 5 and it's m power 4. So what's our the shear stress? Okay, so after all, you will have the 1.887 in megapascal. Okay, what's the mega? Mega is 10 to the power 6. Don't forget the big capital M is 10 to the power 6. Okay, so that's the shear stress at A. Okay, and what about shear stress at B? Okay, and then for calculate the shear stress at B, we don't have to use this formula again because we already mentioned that our assumption is your shear stress is linear along the radius direction. So let's draw this graph again. So this is shear max, and this shear is here, shear is here. Okay, it's grow linearly. It's grow linearly. Okay, so shear stress, shear max is equal to this is radius and this is rho. Okay, so the shear stress grow linearly along the radius direction. Okay, so actually for the shear stress at B, we just use the value at is equal to the shear A and times the R and times the rho B. Okay, so shear stress at A is 1.887 megapascal and times the radius is 0.075. Okay, and radius for the B is 0.015. So the value will be, yeah, you do the calculator, I think it's 1/5, right? 1/5. So 0.377, and the unit is megapar. Okay, so let's calculate for the shear stress at the cross section for a torque loaded member. Okay, actually it's not very difficult. Yeah, you just need to know the term for the shear stress formula. Okay, it's a torque, it's a radius from distance from the center, and the denominator is the polar moment of area. And you also need to know the shear stress of this cross section is grow linearly with along the radius direction. Okay, that's it. Okay, so that's a very simple example. So I don't need too much explanation. So I still record a video for you. Okay, so see you in the next video. Bye bye. Yeah.